Howdy, welcome to lab number 5. I've been Hodge, glider physics, lift. We're going to be proving it using kinetic and potential gravitational energy. Our contents are going to be intro, initial conditions, equations, observed data, simulated data, and a comparison summary, and you can see a cool little picture of the glider that we use in this experiment. Here's the energy sum graph, which is our display of results before the end. The objective of this lab is to demonstrate the conservation of kinetic and potential gravitational energy via forces of lift on a glider, the force of lift being outside the system counting as work done on it. Effectively, we're proving that lift exists similarly to Lab 2's drag, except proving it via conservation of energy as opposed to differences in position. We can also estimate a very rough value for lift force using this method. Our initial conditions are the force of lift and force of gravity acting downwards and upwards respectively, or respectively, and other forces such as drag and friction are not really being considered for this experiment due to smallness and the short time that is measured in. You can see our initial height of 5'11", or approximately 1.6 meters, as of here. Right here, this is 5'11", right here. And our glider is going to be launched and fly for approximately 1.451 seconds. The equations we're going to be using in our lab are the position and velocity update formulas, which we've used pretty frequently throughout, so I don't feel the need to explain them. And our conservation of energy formula, which is the system energy and our work of surroundings, is equivalent to each other in value outside of thermal and other energies lost, but we're not going to be considering them for this lab. This is very important to our core concept, and then our energy and work formulas, which is kinetic and potential gravitational, which since we're close enough to the Earth's radius, we're just going to be considering it on this level and not the higher level. And the important thing is getting the force of lift approximation. We're just going to need to be reversing this work equals force times dot product of the displacement. So here's our video. Click.
Go.
What a kind of variable throw, but that's alright. And you can see us putting it in the tracker here. We are calculating the x and y values based on our positions over here and the height of 1.6 meters, and inputting them and outputting them into this graph, which we can put into an Excel file. We're going to do a similar thing with the simulated data. So for coding, our initial height is going to be 5'11", again, 1.6 meters, again, 5'11" from right about here. Time of flight 1.551 seconds, mass approximately 100 kilograms for tiny people. Velocity 5.51344 meters per second in the x direction. We're not going to be the initial velocity in the y direction is negligible, so we're going to be ignoring it. And then gravitational constant is 9.8 meters per second. We calculated this value being the average change in displacement with the change in time, just for sake of posterity and sake of sanity. Simulated data. Energy calculations, we're going to have kinetic and potential, putting into these respective coding things. We're stealing this from Lab 4, and the most important ones of this particular lab, energy system and equals work surroundings, and we're going to be putting it at 0 for the simulations, not for the actual. For looping, it's the most important part, velocity and position updating over here. The force going into here is just the force of gravity, which we calculated right here, which is ball m times g. And of course, the areas bracketed in orange are dealing with our energy looping. So kinetic and potential being looped over here with their respective formulas, and as such, which were demonstrated up here as well. And our simulated data to a WebP Python code that does this. Ran a little quick there, but you can see that it goes down an angled trajectory due to the initial velocity to the right. Our change in our delta k and delta u gravity cancel out to 0, which is expected for a thing with no external work forcing on it. This is our position, and a bunch of data values we can output in the graphs. So looking at our various graphs, we have a y position graph. You can see that this area is where the plane hit the ground. You can also notice that the glider in the simulated version hit the ground much earlier than this, proving that there's probably a force in between acting upwards. Similarly, for the x position, you can notice the time at which it hit the ground. It's not moving any further forward in the x, which is why they eventually reach the similar amount, because it hit the ground there. As for our velocity graph, you can notice that for simulated increases a semi-exponential line, and whereas this is incredibly sporadic due to the nature of gliders and wind and such. This definitely impacted our kinetic energy graph, which, due to velocity being squared in any of these large increments, definitely increased in magnitude in terms of sporadicness. You can see that the near linear line, the internal kinetic for the simulated kinetic energy versus the very sporadic observed, and similarly for the potential gravitational energy one as well, though this one is a little less drastic, and you can see the negative linear correlation for that. And of course, with our summary and comparison, you can notice that those two linear lines here and here cancel out to 0, which is as expected and simulated, and the observed semi-cancel out. So you can notice that taking all the values of total energy, we can estimate that since this is not a constant, since it is not equivalent to 0, the amount of energy lost is 23.5 joules. Therefore, assuming that all the lost energy is from the work done on the glider by lift, using this formula right here, our work is equivalent to force times change in displacement, calculating change in displacement via the initial and final x and y positions, and dividing this by that value, we get a lift force of approximately 3.039 newtons, assuming that our glider is 100 kilograms, sorry. which is most likely is not. Potential error. Other forms of energy loss, such as heat frictional, sound, quantum, etc., were not considered in this experiment. Coding errors that could have occurred that were oversighted. Excel errors, then graphs that could be present, definitely on those two. Tracker does not account for potential z-depth data, which could have led to inaccurate results. That's most likely true. And also mass errors in assuming that it was 100 kilograms. That's the end. Thank you so much for watching, and I really enjoyed the time making these labs for this class. So goodbye, guys. Bye-bye.